Hi, everybody. It's time to continue our discussion on solar fusion. And we will actually talk about the fusion reaction that's happening in the core of the sun that's producing the solar luminosity, giving us the daylight that we have here, making all the plants grow, and making the Earth a nice habitable world to live on. So let's go ahead and get right to it and talk about the fusion reactions in the sun. It's not going to be as simple as just getting four hydrogen atoms together to form one helium atom. All right. So let's start with the very first step. Let's start with an example of the easiest or the simplest of all the fusion reactions. Let's get two protons together, continuing the example that I had in the previous video of getting two protons together to fuse together to form a deuterium nucleus, a deuteron. So let's take a look so we can familiarize ourselves with a fusion reaction and see what sorts of things come out of it. Because as I was just saying, when we are going to go through the fusion chain reaction in the sun, it's not going to be as simple as just getting four protons together to form one helium nucleus. It happens in multiple steps. It's an entire fusion reaction chain. And this is going to be our first step of the so-called proton-proton chain, which is named for this very first step of fusing two protons together. So let's take a look at that reaction. So we're going to take a proton and we're going to fuse it with another proton. And what we're going to get out of that is a deuterium nucleus, a deuteron. We're going to get a positron, the antiparticle of the electron, just like the electron except with a positive charge, the anti-electron, and a neutrino. So all of those are going to be released during this fusion reaction. And the positron will very likely encounter a free electron pretty soon after it's created. A matter-antimatter particle pair, they get together, they annihilate, and shoot off a gamma ray. Shoot off some light by shooting off some energy by shooting off some light. All right, so that is the reaction. However, it's kind of difficult and it gets pretty troublesome to write out all the words. Proton plus proton gives you a deuterium nucleus, a deuteron plus a positron plus a neutrino. So we usually write it in a shorthand notation. So more conveniently, you could write hydrogen that has one proton and zero neutrons, plus hydrogen gives me a hydrogen that has a proton and a neutron. So we put a two there for two nuclear particles plus a positron plus a neutrino. Or we could use even the symbols for positron and neutrino, stuff that you don't have to remember for this class, but it is a very convenient way to write. It's the only way I can write all the fusion reactions for this presentation. So I could just write this as hydrogen plus hydrogen has a fusion reaction to produce deuterium plus a positron plus a neutrino. And in this case, it's a special kind of a neutrino, an electron neutrino. All right, so that is two protons fusing together to form deuterium. We're not even close to fusing the helium, which is the process that's happening in the sun, fusing hydrogen into helium. All we've done is fuse two hydrogens, protons, into deuterium, heavy hydrogen. To actually get the full reaction, we have to go past this first step. We have to go through this full reaction, chain reaction, or series of reactions, I should say, of fusion that happen in the sun that give us the net result of converting four hydrogens into one helium. And this reaction chain is called the proton-proton chain. Sometimes it's just shortened to be the PP chain. For obvious reasons, I'm going to avoid saying PP chain as much as possible in this class. So the proton-proton chain has three different steps. And in the end, it's going to convert hydrogen into helium, and in that process, release a whole boatload of energy that will power the sun. So the net result is we're going to take four hydrogen nuclei, protons, and fuse them together into one helium nucleus, which has two protons and two neutrons. We're also, as a consequence of each one of these reactions, we're going to produce some neutrinos. Sorry, that says nutrion, it's supposed to be neutrino, plus energy. You know what? I cannot suffer mistakes, so let me just go ahead and fix this. Oh, that makes Dr. Lindsay happier. So we'll get four neutrinos plus energy. And in each one of these reactions, you could go ahead and add up the masses. If you wanted to, you could look up the mass of a proton or a hydrogen nucleus and compare it to the mass of a helium nucleus that has 2 protons and 2 neutrons. So 4 nuclear particles. That's why we put the 4 up there. The helium tells us 2 protons. And then the 4 tells us that, oh, if we have 2 protons, the other 2 nuclear particles have to be 2 neutrons. But you could look at the mass of the helium nucleus and compare it to the mass of the hydrogen nucleus, realize that they're not the same. The 4 hydrogens have more mass than the 1 helium. And you would notice, you could do the math, and you would see that 0.7% of the original mass was lost. So per reaction, per net proton-proton chain reaction, we have a mass loss, a mass conversion of from mass into energy of 0.7%. You will have to get some practice using that number in the homework. All right, so let's go through the full proton-proton chain. It's a 3-step process. We've already talked about the first step, where we're going to have proton-proton fusion, and we're going to do it twice. So we're going to take 2 helium nuclei, or 2 hydrogen nuclei, 2 protons, fuse them together, and we're going to do that twice. So what are we going to get out of this? We're going to get 2 deuterium, one from this and one from this reaction, some neutrinos, and some positrons. So now we have our deuterium. So the first step fuses together to form our deuterium. And we have 2 of them going on. So now we have 2 deuterium. And now we have 2 hydrogens, or really I should say deuterons, and a proton, the nuclei. And now we're going to fuse those together, a deuterium proton fusion, or deuterium hydrogen fusion. Heavy hydrogen and hydrogen will fuse together. So now we have heavy hydrogen, 1 proton, 1 neutron, plus just a proton, fusing together to form helium-3. That would be helium that has 2 protons and 1 neutron. And we're going to, in this process, release energy in the form of gamma ray radiation, a photon. So now we have built our way all the way up to helium-3. And the helium-3 is going to be the input for the next step. So in the next step, we're going to take the 2 helium-3s that we've created, and we're going to fuse those together. So helium-3 fusion. So we get helium-3 fusing with helium-3, and what do you get out? You get 1 helium-4 nucleus, 2 protons, 2 neutrons, and then the 2 extra protons, you get those going back out. So you get 2 protons coming out of this. And guess what? These 2 protons then go meet up with other protons, other hydrogen nuclei, to keep this entire process going. So this gives us a net reaction for our proton-proton chain. This is the part I want you to remember for this class. So what do we get as our net reaction? We're going to take 4 hydrogen nuclei, 4 hydrogens, and fuse them into 1 helium. And then we're going to get some other things out of it as well. Notice that we are producing a neutrino here, we're producing a neutrino here, we're producing a neutrino here. So per proton-proton chain reaction, we're going to get 2 neutrinos out, which is an important part of all the solar fusion things. And I'm not going to make a video on solar neutrinos. I want you to go through the notes and look at the solar neutrinos. There's just too much material to create videos for everything. If people want to request that I make a solar neutrino video, I will. It is an important component, so we do track that. And then we get out our energy. Okay, so this is what you need to remember about the proton-proton chain. I need to go through it in full so you can see what it is, but this is what I'd like for you to remember about our proton-proton chain. We're fusing hydrogen into helium. That can't just happen. That requires a certain temperature where you need a minimum temperature or higher for this fusion reaction to take place. We call that minimum temperature to get a fusion reaction to happen the fusion ignition temperature. Since we're fusing hydrogen into helium, this would be our hydrogen fusion ignition temperature. We need temperatures of at least 10 million Kelvin for the proton-proton chain to even take place. So The core of the sun's a little over 15 million Kelvin. We have the proton-proton chain in the core of the sun, the central part of the sun. And what does a proton-proton chain give us? I want you to remember the net reaction, that we're going to take four hydrogens. Four hydrogens gives us one helium plus energy plus two neutrinos. The neutrinos go out. Neutrinos don't like to interact with anything, so they exit the sun almost immediately, and they go out into the universe, where we can build specialized detectors to capture just a few of them. And through that detection, we can figure out how many solar neutrinos are being produced, and that gives us a different way to probe and investigate the nuclear reactions in the sun that can confirm that this proton-proton chain is happening as we expect in the sun. I have more material in the notes. Please go see all the stuff about neutrinos. So that's what I'd like you to remember. Now let's take a look at the energy that's produced. Let's take a look at all the products right here. So the helium, what happens to it? It's going to stay in the core of the sun. That's where all of these reactions are happening. So slowly over time, the sun is accumulating more and more helium in its core. The core of the sun is changing its composition to become more helium rich. It's increasing the amount of helium relative to hydrogen. It's using up its fuel source of hydrogen to convert it into helium. The energy is mostly going to be produced in the form of gamma rays, and the neutrinos have energy as well. We can't forget that. But the energy that stays in the star is in the form of gamma rays, which, as we talked about, slowly make their way through the radiation zone, then through the convective zone to the surface of the sun, where ultimately they're emitted as visible light from the photosphere of the sun that has a black body temperature of 5,800 Kelvin. And therefore, the photosphere of the sun emits a black body spectrum with a temperature equivalent to 5,800 Kelvin. And then the neutrinos escape without interacting with pretty much anything. There are literally billions of neutrinos passing through us right here at this moment, and they'll go right through the Earth for the most part without a single one interacting with the Earth. They don't like to interact with things. They have no charge, and they have no problem escaping. I think you need a light year of lead to have a 50-50 chance of stopping a neutrino. I think that's the right statistic. Don't quote me on that one. And now let's look at the energy, because we are after what is powering the sun. So we have our net reaction. And notice I've said this several times now. It's almost as if I really want you to commit this net proton-proton chain reaction to memory. Four hydrogens fuse together to be one helium, two neutrinos, and release a bunch of energy. All we need to do is figure out how much mass is lost. So we could look at the mass of the four hydrogens and compare it to the mass of the one helium. And we would see that there's a difference in the mass. The helium has less mass. How much less mass? 4.77 times 10 to the minus 29th kilograms. That's a tiny, tiny mass difference. And you could do the calculation. That's a 0.7% mass loss, which is going to be an easier way to deal with the total energy produced in the sun, as I'll show you here in a second. So per proton-proton chain reaction, how much energy is produced? Only 4.3 times 10 to the negative 12th joules. You don't have to memorize these numbers, but that's how much energy is produced per reaction. That's not very much, right? Times 10 to the negative 12th, that's a tiny amount of energy. But there's a lot of hydrogen in the sun, so this is going to ramp up pretty quickly. So let's consider per 1 kilogram fused into, we have a 0.7% mass loss. So 1 kilogram of hydrogen will fuse into 0.993 kilograms of helium. How much energy is produced in that? So we have a mass loss of 0.007 kilograms. You will produce 6.4 times 10 to the 14th joules of energy. Here's the math of it. Notice it's in green because I don't expect you to do these calculations for this class. But per kilogram of hydrogen, we're going to convert 0.007% of it into energy. So I need to figure out how much mass is going to be converted into energy. So I take 0.007% times 1 kilogram gives me 0.07 kilograms of mass lost in converting 1 kilogram of hydrogen into 0.993 kilograms of helium. That's 1 minus 0.7% of 1. That gives me an energy produced, and you could go ahead and calculate this for yourself if you don't believe me. Plug it into the E equals mc squared, 6.4 times 10 to the 14th joules of energy per kilogram of hydrogen in the sun. To power the entire solar luminosity, that ridiculously large number of 3.828 times 10 to the 26 joules per second, produced every second, we would have to convert 6.1 times 10 to the 11th kilograms. 610 million kilograms of hydrogen are fusing into helium every second in the sun. So you can calculate the mass loss of converting 6.1 million kilograms. That would be 0.007 times that number. Use that in E equals mc squared, and you get the solar luminosity. That gives you a way to calculate how much fusion has to be occurring in the sun. This tells us the fusion reaction rates, how many kilograms of hydrogen are being fused into helium every second in the sun. That gives us the solar luminosity. It also gives us a way, we know how much mass we have in the sun, so we know how much hydrogen fuel we have to be converted into helium. And we know that the sun is 5 billion years old by the age of the solar system. And so we can go ahead and figure out, oh, well, how long until the gas tank of hydrogen runs out, until the core of the sun is converted from hydrogen entirely into helium? So we can keep this proton-proton chain happening, fusing hydrogen to helium in the core of the sun for another 5 billion years, at which point the sun is going to start dying. And that's going to be a subject for a little bit down the road whenever we talk about the death of stars. We have another 5 billion years where the sun can happily maintain its solar luminosity via the proton-proton chain by fusing hydrogen into helium in its core. That's what I had for you in this video. Next, we'll change gears a little bit, and we're going to be talking about the magnetic activity of the sun, the activity on the sun, things like solar flares, solar prominences, sunspots, the sunspot cycle. I will see you in those videos as we wrap up the sun.